Over 5,000 extrasolar planets have been discovered. But what then have we learned? Billions of red, yellow, orange, blue, and white stars glow in space at distances measured in millions of billions of kilometers, thousands of times farther than our solar system's most distant planets. There is no doubt that mankind has strived to comprehend the universe from the dawn of conscious cognition. Armed with evidence of the presence of planets surrounding other stars, scientists are now asking more specifically, what are these worlds like? How many planets are there among the 100 billion stars in our galaxy, the Milky Way? And how many of those planets are simply barren deserts or cold hydrogen spheres? Are any of them home to vast forests or abundant oceans? Astronomers can now begin to address these questions for the first time in history. Michael Mayer and Didier Queloz, two astronomers, discovered the first extrasolar planet, 51 Pegasi b, around the star 51 Pegasi in 1995, a gas giant planet with Jupiter-like dimensions around a Sun-like star. Moreover, 5,000 exoplanets have been identified to date, and the number is still growing. The advancement of observational tools and the introduction of dedicated spacecraft missions have made the search for exoplanets, particularly those with good circumstances for life, one of the most fascinating topics in astronomy. However, how do we find these planets? What is their makeup? What instruments and missions are planned over the next few decades? Finally, will it be feasible to discover other livable planets? The goal of this film is to answer some of these questions while also inviting you to contemplate the magnificent and mysterious beauty that surrounds us. Hello and welcome to Zeey. Subscribe the channel and ring the bell not to miss our daily videos. There are 5,382 confirmed exoplanets in 3,974 planetary systems as of May 24, 2023, with 858 systems having more than one planet. The majority of them were discovered by the space telescopes Kepler, active from 2009 to 2018, and TESS, active since 2018, as well as the European Cheops, active from 2019. However, there are 9,618 more waiting to be confirmed in the archives. So even if fresh discoveries ceased, the total number of extrasolar planets already found may reach around 15,000 very soon. Isn't that good? A lot has happened in less than 30 years since that day in 1995. And it appears that the future will bring us even better chances, albeit the route will become increasingly difficult as the distances we must travel rise. Indeed, objective perceptual issues impede the hunt for extrasolar planets. It is, in fact, a matter of contrasting a very small and poorly lit body, the planet, with a very massive and extremely bright one, the star akin to detecting a moth circling in the light of a street lamp from a distance of several kilometers. The star appears to be a billion times brighter than the nearest planet, rendering the latter undetectable due to the dazzling glare. However, if the observation were made in the infrared rather than the visible spectrum, it would be discovered that the difference in brightness between the two bodies is only 10,000 times, a value that is still very large, but which, in the best cases, would allow the planet to be distinguished from the star. Furthermore, the two heavenly bodies are frequently so close together that even the most powerful earthly telescopes cannot distinguish them. A planet like Jupiter, for example, would appear to be separated from the Sun by only half an arc-second at a distance of 10 parsecs, about 32 light-years, practically in close contact with the star and barely distinguishable from it, and 10 parsecs is a minimal distance in the vast cosmic space. Finally, if the central star's mass to that of a planet like Jupiter is roughly 1,000, it is more than 300,000 compared to Earth, and therefore the gravitational perturbations that our planet would exert on an average-sized star would be minimal. This is also why only planets of significant size and quite near to the star they circle have been identified thus far. How do astronomers find new exoplanets? There are primarily indirect and direct techniques. The solar system was the sole extant model of a planetary system until the 1990s. We didn't even know whether planets orbited other stars. As a result, we had no idea what mass and size combinations these unknown planets were orbiting their stars in. But everything changed in the second half of the 1990s. With the introduction of digital technology and the advancement of optical technology, we amassed solid evidence supporting the presence of thousands of exoplanets in a little more than 2 decades, mostly through 2 methods. This has resulted in the creation of a large database of planetary objects, an astronomical zoo populated by various types of planets, some of which do not exist in the solar system, such as super-Earths and hot Jovian planets. Super-Earths are exoplanets with masses 2 to 10 times that of Earth, and they are thought to be rocky like our planet. Hot Jovians, on the other hand, are gas giants that are hypothetically similar to Jupiter but orbit very close to their stars in a hellish dance that was not thought possible because planetary formation theories suggest that Jupiter-sized planets can only form far from their stars, beyond the so-called ice line, the temperature at which water can only exist in icy form. Earth-like worlds are at the bottom of the scale. Bodies with varied quantities of silicates and water, but no prolonged envelope of volatile elements, may have an atmosphere, but it is rather thin, and there is always a solid surface underneath it. This category includes true rocky planets. Their radius is less than 1.25 times that of the Earth, and their mass ranges from 0.1 to 2 times that of the Earth. So far, 198 have been discovered. The Neptunian worlds are the following category. The solar and extrasolar planets in this group differ from Earth-like planets in that they retain massive helium and hydrogen atmospheres due to their greater gravity. Even if they had a solid surface, the massive gaseous layer enveloping it would produce insufferable pressure for any kind of life, spanning for thousands of kilometers. Saturn, with its 95 Earth masses and extremely low density, is at the higher end of the Neptunian world group. 1859 have been discovered and confirmed to date. The third group is the Jovian worlds, which are gas giants consisting primarily of helium or hydrogen. These planets, like Jupiter and Saturn in our solar system, have swirling gas over a solid core rather than hard surfaces. Exoplanets that are gas giants can be substantially larger than Jupiter and much closer to their stars than anything in our solar system. So far, 1707 of them have been discovered. Is there anything out of the ordinary about our solar system? Or do we still know too little about extrasolar planets to accurately classify them? Perhaps both, but the latter seems more plausible. Let's see why. To determine the nature of an exoplanet, such as whether it is rocky or gaseous, 2 pieces of information are required: mass and radius. The density of the Earth, a rocky planet, is 5.5 g/cm3. Saturn, a gaseous planet with no solid surface, has a density of only 0.7 g/cm3. Between these 2 extremes are all the bodies in the solar system, moons, planets, and asteroids that are large enough to have adopted a nearly spherical shape due to their own gravity. We know the density of each precisely because we know the radius and mass of each with equal precision. Unfortunately, we don't know as much about the great majority of exoplanets. We know either their radius or their mass, but not both. The radial velocity approach calculates the mass of a planet, with approximations due to our knowledge of the orbit's inclination from our point of view, whereas the transit method calculates the radius of a planet. Only in exceptional circumstances can we employ both methods, transit and radial velocity, to gain precise knowledge of both the radius and the mass. In all other circumstances, when only one of the 2 components is known, determining the kind of planet is totally hypothetical, though based on acceptable assumptions. However, as equipment sensitivity improves, new ways for characterizing newly discovered planets emerge. In the case of planets that eclipse their star, for example, spectroscopy allows us to see a difference in the system's spectrum, which is the sum of the stars and the planet's spectra, when the planet is hidden by the star and when it passes in front of the stellar disk in some cases. This difference can only be traced to the planet and thus offers information about its chemical composition and temperature. Similarly, variations in the system's infrared radiation during the planet's revolution around the star provide information about the different surface temperatures of its regions depending on the illumination, day-night alternation, allowing us to infer its surface temperature and the presence of an atmosphere. Continuous improvement of these measurement techniques may one day give us with hints about the existence of living forms. Geologists, for example, promise us that the amount of oxygen in the atmosphere is a reasonably certain indicator of the presence of life. In fact, oxygen is an extremely reactive gas that easily combines with other elements to form oxides and anhydrides. Without plants that continuously manufacture it by decomposing carbon dioxide, the Earth's atmosphere would lose all of its oxygen within a few million years. As a result, the discovery of oxygen in an extrasolar planet's atmosphere would be a good indicator of the presence of life on it. Yes, more of the same about the search for life. It is an addiction we will never be able to shake, not just for the dream of one day looking into the eyes of creatures identical to ourselves, but also for the legitimate desire to seek livable planets for the future of our race. Astronomers must hunt for Earth-like planets that are neither too cold nor too hot, and that are temperate enough to support water, which is the mixer and solvent of organic chemistry and biochemistry. Planets with the ideal molecular composition, orbiting their sun at just the proper distance, have what astronomers call a Goldilocks orbit. If we came upon such a planet, we would be bombarded with questions. Is its atmosphere composed of oxygen, nitrogen, and carbon dioxide, like on Earth, or of sulfuric acid and CO2, as on Venus? Is there an ozone layer to shield the surface, or is it burnt by dangerous ultraviolet rays? Will the pH of a planet's water be neutral enough for cells to flourish even if it has oceans? Furthermore, even if primitive life had flourished on another planet, is it certain that it would always result in intelligent life forms, or is human technology simply a stroke of Darwinian luck? Are we a unique piece of nature, appearing only once on an Earth-like planet in a universe otherwise filled with primitive life? Surprisingly, some of these issues are likely to be solved within our lives. It's difficult to anticipate what we'll learn by the end of this decade using devices that are currently in place, such as the Webb telescope, or that are in the planning phases, such as the European 39-meter telescope under construction in Chile's Atacama Desert. Yes, because our species' destiny is to explore the galaxy and discover its biological and chemical roots among the stars. What do you think, guys? Is there anything we left out? Tell us in the comments and don't forget to like, share, and subscribe.